And now we continue with the title, Recent Developments in AdS3 CFT2 Integrability by Davide Polvara. Please.
Does it work? Yes. Okay, let me thank the organizer to having given me the opportunity to speak here in this nice conference. And today I would like to speak about some recent work I've been done together with Alessandro Sfandrini and Sergei Frolov, which are both in the audience. In particular in the past 2 years. And what we did was to try to bootstrap the complete worksheet as matrix of superstring which propagate in this background, AdS3, in the presence of mixed flux. So let me give an overview of integrability in the context of AdS-CFT, which is our motivations. And as you probably know very well, there is this correspondence, which is AdS-CFT, and there is a particular limit of the correspondence in which the theory on both sides of this correspondence becomes integrable. So we have 2 parameters on the left-hand side. There is type 2b superstring theory, which propagate in AdS5 S5. And these 2 free parameters are basically the string tension and the string coupling. And on the other side of the correspondence, you have a connection with other 2 couplings, which are the tooth coupling and the rank of a gauge group. And if you take the rank of a gauge group to becomes very large to infinity, so which is the planar limit of n equal 4, or equivalently you take G strings to be 0, so you consider strings which freely propagate in AdS5 S5, then you have an integrability descriptions of a theory, which means if you consider, and in particular in this talk I will focus on the left-hand side of the correspondence, if you consider these strings which propagate, the theory on the worksheet is a chiral models and as an S matrix which can be exactly found. And the first signals of integrability were found by Jominan and Zarembo here, I think, in NORDITA in the 2002. So what is integrability? The idea is that you have a large amount of conserved charges, and in particular on the worksheet theory, you have this large amount of conserved charges, which forces the scattering to be diagonal and factorized. What this means is that if you consider 2 fluctuation which moves on the strings, which here I put like a red and a blue fluctuation with 2 masses, after the scattering, you still have the same masses for your particle. So if you can have in principle a supersymmetric multiplet, so you can have a reshuffle of particles, but you don't have, for example, productions of particles, so you still have the same type of particles after the scatterings. And then there is a systematic route starting from the S matrix, which means you consider the worksheet to be very large, and you have a notion of asymptotic state of your theory, to bootstrap the S matrix. And starting from this S matrix, you can try to quantize the string, which means first you go to large and periodic worksheet, and you do what is called asymptotic beta ansatz. But then if you want to quantize the string at finite length, what you need to do is to derive what are called thermodynamic beta ansatz equation, which keep into account basically also wrapping correction around this string also at finite volumes. And after a large number of, say, again, non-trivial steps, which is the derivation of Y system, T correlation, so on and so forth, you can end up to what is called a quantum spectral core, which is the modern method, say, more modern method to find the spectrum. Now, what we want to do is to repropose kind of the same approach for a different setups, which is AdS3 S3T4. And in particular, in this case, you have half of a supersymmetry compared to AdS5 S5. And it's a quite interesting since this background dates back to the early day of holography. And it was discovered by Cagnazzo and Zarembo that the family of principal chiral model and chiral model that lives on the worksheet of the strings are classically integrable. And in particular, in this case, you have also fluxes, differently from AdS5 S5. You have, in principle, 2 different parameters. One parameter is the amount of Nevers-Schwarz flux, which I labeled by K here. And the other one is the amount of Ramon-Ramon flux. So the first one is quantized, can be 0, 1, 2, and so on and so forth. The other one is a continuous parameter. And some of these backgrounds are well known. For example, if you consider pure NSNS flux and no Ramon-Ramon, then the theory on the worldsheet is a Vezzumino-Witte model of level K, and the spectrum can be exactly found by CFT methods. On the opposite side, you can have 0 NSNS flux and pure Ramon-Ramon. In this case, basically, the Vezzumino-Witte construction breaks completely. You cannot use RNS formalists to the quantization of the string. And in this case is where integrability really enters into play. And this, say, thermodynamic Betances equation and quantum spectral curve were derived independently by two different groups, one by Frolov and Sondrini and collaborator, and the other ones basically by Simone Camar, which is here in the audience, Nikolai Gromov, Cavaglia, Stefanski, Torrielli, and Volin. And basically, you can use both sides of this arrow are two separate sets of equations. Still, we don't know exactly how to match them, but can both be used to derive the spectrum of your theory. And then there is the most mysterious case, which is the case in which both the Ramon-Ramon flux and the NSNS flux are different from 0, which is what I want to speak about in this talk. And in particular, what you have an action, is a nonlinear sigma model in which what appears in this action is the extension of the strings, T, and certain B field, which multiply basically this quantized amount of NSNS flux. And the two parameters I speak about before are this H and this K, which are both connected to the string tension. So these are my parameters of my theory. I want to describe the theory at any values of these parameters. And there is an interpolating family between the pure Ramon-Ramon case and the pure NSNS case. Okay, so this is the overall setup. So the plan of the talk will be to the derivation of the S matrix for my theory, both massive and massless S matrix, for the fluctuation of these strings. And then I will explain you what checks we did to prove, or at least have confirmation that our bootstrap results are correct. And then I will tell you about some future direction that we would like to pursue. Okay. So let me start with massive S matrix, first of all. So what we have some theory on the worldsheet, and in particular we have 3 coordinates on AdS3, 3 coordinates on the sphere, and 4 coordinates on the torus. And what we want to do is to do some Lycon gauge fixing, which means you want to impose some Virasoro constraints, and we want to remove also all the redundant degrees of freedom of the theory, which means you don't do some conformal gauge, but we do some Lycon gauge. And after this Lycon gauge, the theory is not conformal anymore. You break conformality, and you also break Lorentz invariance. And in particular, if you start with 10 bosonic coordinates, you end up with 8 of them, which survive this quantization, which are all physical. You don't have any ghosts propagating on these strings. And if you study the supersymmetry realization of this theory, what you have that at the massive level, so there are in total 8 massive particles in the theory. So this Y here and this Z comes respectively from the sphere and from AdS3. And on the other side, you have another supermultiplet of your theory in which there are Z bar and Y bar appearing. And the superalgebra, the gauge-fixed supersymmetry algebra of the theory is PS1, 1 to the 4, which was derived in the past by Borsato, Olson, Sachs, Sondrini, and Stefanski. And in particular, there are some exact dispersion relations for the energy of your particles. So as you can see on the left-hand side, I label the energy of my particle by E left. And here appears both the amount of NSNS flux and both the amount of Ramon-Ramon flux. P is the worldsheet momentum, and this one here corresponds to the mass of my particle, a certain quantum number that you can associate to the mass. On the right-hand side, you have exactly the same dispersion relation, but instead of having 1, you have -1. And what was done in the past was to find out what is the supersymmetry algebra of these models. And the idea of integrability is that if there is an S matrix which scatters the different particles of your theory, then this S matrix must commute with all the supercharges of the theory. So if you have some symmetries, and since the other symmetries must commute with your S matrix, which means that the S matrix is almost entirely fixed by just symmetry considerations. What is not fixed is an overall multiplicative factor. So of course, if you have two matrices that commute between one another, you can still multiply one of the two matrices by some function, and still these commute between one another. And to fix this orange parameter, which is called dressing factor, you need to add some extra physical input, like for example, unitarity, crossing, nice property under fusion. And this dates back basically to Zamologico and Zamologico when they attach this problem for a relativistic integrable theory. Here, I study a non-relativistic theory. And more specifically, what you have two different representations, one that I call left and one that I call right. When you scatter particle, you can have some reshuffling of particle in the representation. So if you start with two white particles, say, after the scattering, you can have that what comes out are two particles of type Z or some other particle inside this multiplet, but you cannot end up with two right particles. So the scattering is completely elastic at the level of these representations. So basically you have four different dressing factors, sigma left-left, right-right, left-right, and right-left, which are not fixed, because are this fact that you have, in principle, four possible different scattering between different representations. And what we did was to constrain basically these scalar factors, which I will not go enter into this particular discussion. Let me just say that there is a part of the scalar factor which is called odd for historical reason, which was obtained by Olson, Sachs, Rybchenko, and Stefanski. And what we did was to add to their solution the missing piece, which is what contain basically the BS dressing factor, the part which comes from Eiser-Eden and Stabdacher for radius 5s5. Here we propose a generalization of these dressing factors also for this setup. And this is particularly interesting because basically it admits very non-trivial dynamics of the model. So okay, I will not go into it, but it admits a very interesting integral representation, for example, with Diego Hoffman, Maldacena, and Nick Dory. And to describe exactly what is this dressing factor, you should introduce, for example, what is the boundary between physical and unphysical region of your particle, where the energy is positive, where the energy is negative, and allow you to solve crossing. So once you find out what is the S matrix of your theory, you still need to use this S matrix to find the spectrum. And the idea is that we start from string region. So you take the limit in which the worldsheet is very large, and you have a notion of asymptotic state, but then you want to go to the case in which the worldsheet is finite, at a finite length. And to quantize the string, when you go to finite length and keep into account all the wrapping correction, you should derive a thermodynamic Betances equation of your theory. And Zamologico in the 89 teach us that basically what you can do to quantize a theory of finite volume, this is equivalent to the quantization of theory at infinite volume but finite temperature, in which case the temperature is the inverse of your volume. So if you have a torus, in particular, you can associate it to one of the cycle of the torus to the time, and to other cycle of the space, but you can also do the opposite, and there is a connection between these two sides. And the idea is that if you have a time and some space on the worksheet, you should do some double weak rotation, in which case you send the time to I sigma, to I space, and sigma to I tau. So you do this double weak rotation. And at the level of the energy of the momentum, this corresponds to send the energy to IP and the momentum to IE. So if you have some relativistic S matrix, by doing this double weak rotation, so suppose you have some relativistic special relation of a form E square minus P square equal M square. By doing this transformation, you still obtain the same type of dispersion relation. And the S matrix is still the same for a relativistic theory. But if a theory is not relativistic, like in this case, I have this complicated dispersion relation, when I do this double weak rotation, say I obtain a dispersion relation which is quite different compared to the original one. And the S matrix that you find on the string theory must be analytically continuous to this mirror region in a non-trivial way. So what we did was to study this S matrix both on the string region, what we call string region, and on the mirror region. And in particular, we checked that all the properties that were expected to be satisfied, because we knew the Lagrangians both on one side and on the other side, were actually satisfied. For example, if you consider parity, parity is a property which is valid in the mirror region, because if you consider you start with the Lagrangian of a string region, you do this double Wick rotation, so you obtain the Lagrangian of a mirror region. You will observe that sending sigma tilde to minus sigma tilde, the Lagrangian is left invariant. And you expect then the model should be parity invariant in principle, unless you have some anomaly at quantum level. But we don't want, so in principle we want to preserve parity for the mirror model, and you observe indeed that at the level of S matrix parity is satisfied. So what does it mean? This, it means that if you have an S matrix, you are reflecting in a mirror, you are just one dimension, so if you scatter P1, P2, this is equivalent to the scattering of minus P2 minus P1, basically. And this is a property which is satisfied at the mirror theory side, is not satisfied on the string theory side. What should be satisfied on the string theory side is a time reversal symmetry, basically, because sigma and tau are connected by the mirror transformation. And once you have the S matrix for your fundamental particle, and here I'm describing the scattering of fundamental particle, you can also derive what is the S matrices for the bound state. And this is also an idea that is very well known at the level of for integrable theories, which means if you have more particle which compose a bound state, so if suppose you have some bound state of mass m, which for fundamental particle m is just 1 or minus 1, but for bound state can also be plus minus 2, plus minus 3, and so on and so forth. So if you have, for example, m equal 3, means that this is a bound state composed of 3 fundamental particles. And to obtain the associated S matrices, you should multiply themselves as matrices of a fundamental particle composing the bound state. And the momenta of these constituent particles are chosen in such a way that the overall energy momentum conservation is satisfied for this bound state. But in principle, you have all the S matrices. And these are also obtained in a closed form in the paper, anyway. Additionally to the massive representations, which I was speaking before, there are also some massless representations. In particular, there are 2 massless multiplets, which comes from the fluctuation on T4 for this background. And this massless representation contains some index, A dot, which is an SU2 index. So you have 2 of these, basically, massless multiplets. And the S matrix contains a piece, which is the piece of a supersymmetric multiplet, which contains some reshuffle of the particle inside these supersymmetric multiplets, but also describe the scattering between the 2 different multiplets. So before I was saying that for left and right representation, for massive representation, we scatter completely elastically. In this case, in principle, you can have also some reshuffling between these 2 multiplets. And this SU2S matrix perturbatively is expected to be just the identity. This is just a perturbative result. Apart from perturbation theory, you don't have any other confirmations. But our approach was to try to force this SU2 additional S matrix to be exactly equal to the identity also non-perturbatively. And the way in which we found this matrix for this massless fluctuation, basically starting from the massive one, and then taking the mass of our particle to 0. So in principle, if you associate one of the 2 massive multiplet, one of these 2 massless representation, and for the other one, the second massless representation, you take the m to 0 limit, and you obtain, starting from the crossing of this massive representation, the crossing equation of the massless representation. And okay, this was just a side comment, which I will not go into much detail. So once you have the S matrix, you still need to have, in principle, you can have some CDD ambiguity. So you're still not sure that the matrix is correct. So you still have a solution which satisfies all your symmetry requirements. But the solution in principle could be multiplied by some extra function which just satisfy all these requirements, in particular which does not affect, for example, parity, crossing equation, and all your symmetries. These are called CDD, and Roberto Tateo, I think yesterday, gave an overview of this CDD factor. For example, TT bar introduced this type of ambiguity. So what we need to do is still to try to have to be sure our answer is correct. We need to confirm this result in different perturbative regime. And in particular, what we did was to check that in the largest intention, in what is called BMN expansion, the result agree with perturbation theory. And it does, both at 3 level and also at 1 loop, regarding the cut constructable part of the amplitudes. What does not, there is a disagreement for the part which is not cut constructible. And in this case, we believe that this disagreement is due to some counter term that should be added to the Lagrangian to have some, for example, to provide purely elastic scattering at 1 loop order. The other regime that we considered was a particular relativistic limit, which was studied in these 2 papers, both by me, Frollo and Sondrini, and also by Fontanella, Sask, Stefanski, and Torrielli, in which case, basically what we do is to consider the dispersion relation of our theory. So these are kind of very complicated dispersion relations. But then what you do is to consider the amount of Ramon-Ramon flux to be very small. So if you consider this H to be very small, it happens that this dispersion relation from this fluctuation, very ugly fluctuation dispersion relation, becomes basically a kind of a cusp. And you expand around the minimum, the global minimum of a dispersion relation, with fluctuation of order H, so the same order of a Ramon-Ramon flux. If you do so, you obtain that starting from this complicated dispersion relation, you end up with the dispersion relation of a relativistic theory, in which case, basically, you can solve completely the bootstrap in this particular relativistic limit. And this is really identical to what Zamolodchikov and Zamolodchikov did. It's very established approach, in which case you have a notion of what is a physical strip, rapidity, and so on and so forth. But then we want to compare that the S matrix that you find in this particular limit is the same as matrix that you obtain by taking the limit of a full solution of our full S matrix here. And this is a check that we did, and we obtain exact match for this particular case. So we believe that the answer should be correct. So what are the future directions? So one of the interesting things to be done at this point is try to take K finite and send H exactly equal to 0. So in particular, once you have a complete S matrix at any value of a Ramon-Ramon and Never-Schwarz flux, you can use the S matrix to find the spectrum. And there are some particular points in which the spectrum is known. And one of these points is the case in which you don't have any Ramon-Ramon flux, you just have pure SNS. And this is the Zumino-Witten construction. So it would be interesting to see if at this particular point you can reproduce exactly the spectrum of the Zumino-Witten model. And then the question is also what happens if you take, for example, k equal 1 and you consider a small amount of Ramon-Ramon flux, in which case there is conjecture, or there is a proposal for what should be the dual conformal field theories. And this should be the symmetric product orbifold theory, which I write here. It is by a paper by Eberhard, Gaberdiel, Nopakumar, and different groups have studied also deformation around the symmetric product orbifold point, and who be interested in trying to match what are these results from the worldsheet theory point of view. Of course, you can try to solve a spectrum numerically at all value of H and K. This would be very tough and difficult problem, but in principle can be achieved. And also would be interested to try to derive, starting from our TBA equation for this matrix, what should be the quantum spectral curve equation. This connection is still lacking, also for the pure Ramon-Ramon case, so this is still work in problem also for the case in which K is equal to 0, but is for sure a very interesting direction, and to have a completely control on the numerics. And then in general, you can try to promote T4 to some more generic manifold. For example, S3S1 is also one of the manifold which should be integrable, and Fiona Seibel yesterday mentioned about this. So there is an entire class of integrable theory and deformation of this integrable model which still remain to be explored at the quantum level. This is one of the most simplest examples which we would like to solve completely. So I will conclude here. Thank you for the attention.
Thank you. Questions and comments? Welcome. touch. Okay, let's then thank David once more for the nice talk.